to the Crazy Fat Chemist. So another video here on Thermochemistry 2. So let's get moving. Bam! So today we are talking about equilibrium constants and Gibbs Free Energy. So there's a mathematical equation that ties in both Gibbs Free Energy and equilibrium constants. We have spent an entire unit on equilibrium constants, and that is KEQ is products over reactants with the stoichiometric coefficients as exponents. Solids and liquids need not apply. So make sure at some point in time, if you're in this unit right now, you review the equilibrium unit, the entire unit. It's an awesome unit. It's so essential to every other future unit. Acids and bases, this unit here on thermochemistry, and then another unit on another topic. So let's keep on going with this problem. Here we go. We're going to determine the equilibrium constant, that's the KEQ, given the delta G naught for the combustion of methane. So the first thing that we need to do is figure out what is the formula for methane. Methane is natural gas. Methane is the simplest hydrocarbon. So the simplest way that I can get you to this answer is write a carbon down, just a single C for carbon. Then do a Lewis dot structure with hydrogens. Write as many hydrogens on there as possible as the rules dictate. And then you will get the formula of methane, which is CH4. And that is a gas, like I said, it's natural gas. Then it says the combustion of methane. So now I need to figure out what is the other reactant that is necessary for a combustion. So if there's a fire, you're going to use a fire extinguisher to put it out. And that is essentially like carbon dioxide or maybe some other foam to remove what? Or you can take like a wool blanket and smother the fire. So what are you removing when you throw that wool blanket over the fire or using a fire extinguisher? You're removing the molecular oxygen, the same stuff that is necessary for us to breathe in. And because essentially all we're doing is a combustion reaction ourselves inside. Okay? So the necessary other component is molecular oxygen. Now I need to figure out what is the formula for molecular oxygen. So in order to do that, you need to take your right hand and give me one of these symbols. Put it right on your forehead and think to yourself, am I a... No, you're not a loser. Okay, this is just to remind you that you got an L on your forehead. You're going to flip it down. You're going to ask yourself, what is that number that I see right before me? I see the number 7. So that lets me know that there are 7 diatomics. There are 7 metalloids, and there are 7 strong acids. Just like if you were to go to Vegas, baby, you're going to pull that lever and get 777 for 7 diatomics, 7 metalloids, and 7 strong acids. But I'm here to talk to you just about molecular oxygen and the formula for molecular oxygen, which is O2 because it's a diatomic. That's a 2-atom molecule. So now you have our 2 reactants. That's CH4 and oxygen. Now, it's a combustion reaction with a hydrocarbon. So there are always the same set of products for any type of hydrocarbon combustion reaction, and that would be carbon dioxide and water. Now what you're going to do is you're going to balance the equation. You're going to pause the video, balance the equation, and then restart it. There's the answer. So hopefully you got that. That's 1 mole of CH4, methane, plus 2 moles of molecular oxygen yields or produces 1 mole of carbon dioxide and 2 moles of water. Okay? Now, you can get the delta G for this reaction all on your own. That's also something that you should be doing. Okay? You should get the delta G from this, and you can do it one of 2 ways. Maybe try it both ways. One of them is using the table of thermodynamic values and the delta G naught of formation. Products minus reactants. Or the other way is to calculate the enthalpy for this reaction and then the entropy for this reaction, and then use the equation delta G equals delta H minus T delta S. That will also yield the same answer, which is this answer right here, which is negative 818 kilojoules. Now, something that you should know with this numeric value is the sign. The sign is the most important thing. And you know that sign lets us know that this reaction is spontaneous. I cannot tell you anything more about this than this reaction is spontaneous based on that negative sign. All right, So now we need to use the equation that's going to correlate the delta G and the equilibrium constant, and that is right here. So delta G is equal to negative RT ln KEQ. Okay, the delta G is the Gibbs free energy equals negative, the R is the gas constant. We have used that before. We're going to use a different version here with the correct set of units. T is the temperature. Ln is a natural logarithm. That's a mathematical function. Hopefully you've done your Algebra 2 or your pre-calculus class. And the KEQ is the equilibrium constant expression. That's products over reactants, stoichiometric coefficients, that's exponents. What we're going to do now is plug in the values into this. We're going to plug in the value for the delta G. We're going to plug in the value for the R. We're going to plug in the value for the T. And we are not going to plug in a value for the natural log because that's a mathematical operation. And the KEQ is what we're solving for, so we're going to leave that alone. Here it is plugging in all those values. Having plugged in those values, you should see on the left-hand side I've done a little bit of unit conversion. I've converted my kilojoules into joules. And that will make it so that it will coincide with what's on the right-hand side with the gas constant, which is also in joules. On the left-hand side, I have negative 818 kilojoules per mole. Now, the per mole part is because I'm calculating the combustion of methane. So what is my denominator term? My denominator term is actually a 1 because the stoichiometric coefficient on methane is a 1. If I were calculating the combustion of, or if I were doing the calculating the KEQ for oxygen, then I'd be using a 2 right there because there's a 2 stoichiometric coefficient on the oxygen. If it were the carbon dioxide, it would be the 1. If it would be the water, it would be a 2. Okay? Hopefully you've got that. So the left-hand side, I've got my delta G converted into joules. On the right-hand side, I got my negative sign. I got my R value at 8.314 joules per Kelvin mole, and my temperature of 25 degrees Celsius converted into Kelvin at, so that would be 298.15 Kelvin, natural log KEQ. Let's do a little bit of math, canceling units, and simplification right here. On the left-hand side, I have negative 818,000 joules per mole is equal to negative 2,478.8 joules per mole times the natural log of KEQ. We're going to move that numeric value over with a little division here and cancel out our units. Bam! I got 328.995 is equal to natural log of KEQ. Now, I'm hoping you remember back to your math. Addition, subtraction, multiplication, division, natural log, and e to the. Okay, so what we're going to do is we're going to take e to both sides to get rid of our natural log term on the right-hand side, and that will isolate our KEQ. Okay, and that's what I've done right here. So natural log, e to the natural log of KEQ is going to be the KEQ, and then e to the 329.995, that's going to be a numeric value. So now I have the KEQ is equal to 2.067 times 10 to the 143. That's an enormous number. It's very close to my yearly salary. Not. Okay, so what I want you to do is I want you to look at the delta G value at negative 818, really the negative portion of it, knowing that that is spontaneous. Okay, so that value is less than 0, right? Because it's negative. And then look at the KEQ. The KEQ is a positive exponent and it is greater than 1. So there's a high correlation between the Gibbs free energy and the equilibrium constant. And that's what we're here learning today. And so this is what we are learning. We are learning that when the KEQ is greater than 1 and the delta G is less than 0, the two of those coincide together. It's spontaneous and product favored. All spontaneous reactions have a delta G of negative. All spontaneous reactions have a KEQ that's greater than 1. All product-favored reactions have a delta G that's negative. All product-favored reactions have a KEQ that is greater than 1. Awesome. Let me show you another example on the flip side. Here we go. So we're going to determine the equilibrium constant, that's the KEQ, given the delta G for the decomposition of calcium carbonate. So what I want you to do also is get the formula for calcium carbonate. Calcium is a group 2, it has a 2+ charge. Carbonate is a polyatomic ion with a 2- charge. That's actually in a 1-to-1 ratio. So now I have calcium carbonate, that's a solid. That's the only reactant since this is a decomposition reaction. That means it's going to break apart into two things or more. Okay, I want you to write down what you think the products are. This is a really simple balancing of equation once you do have the products. And here we go. There's our equation. So calcium carbonate decomposes to calcium oxide and carbon dioxide. Okay, the delta G for this one should also be something that you should be able to calculate using a table of thermodynamic values of either delta G's or the enthalpy and entropy values, and then calculating the delta G. Okay, notice that this delta G here is positive. That makes this reaction non-spontaneous. And so now, knowing from the previous reaction that we did, you should actually be able to predict what the numeric value is and the size of that value for the KEQ based on the delta G for this reaction being positive and knowing what you learned in the previous slide. Okay, so let's do the math associated with this and write down that equation that correlates and associates delta G, Gibbs free energy, with the equilibrium constant. That's right here. Delta G is equal to negative RT ln KEQ. All right, so now what we're going to do is we're going to plug in our values into this of what we know, and we're going to solve for the KEQ. So we've got on the left-hand side 130 kilojoules per mole times the 1,000 joules per kilojoule. That will enable us to cancel out the kilojoules. On the right-hand side of the equal sign, I have a negative sign. I got the gas constant at 8.314 joules per Kelvin mole times the 25 degrees Celsius in Kelvin temperature, and that would be 298.15 times natural log of KEQ. A little bit of simplification, unit canceling, and you do know that this is a 1, and that's why that denominator is a 1, and in fact it would be a 1 for anything within this equation. So a simplification, unit canceling, and this is what I have. So I got 130,000 joules per mole is equal to negative 2,478.8 joules per mole times natural log of KEQ. I'm going to simplify even further and move both the numbers to the left-hand side. Now I have a negative 52.444 is equal to the natural log of KEQ. And again, what's the opposite mathematical function of natural log? It's e to the. That's that lowercase e that's on your calculator. So I'm going to take the e to both sides, and that's what I'm going to get. When I take the e to the natural log disappears, and I'm going to have the KEQ on the right-hand side. And then e to the negative 52.444 is going to actually equal a numeric value. So that's what I have right here. I got KEQ is equal to 1.674 times 10 to the negative 23. That is a very small number. So now you should be like correlating the KEQ value as a very small number, less than 1, with that delta G value as a positive value greater than 0, and then associate this information here. For non-spontaneous and reactant-favored reactions, you should have a KEQ that's less than 1 and a delta G that's greater than 0. Okay? I've done both sides of this coin. I've done a spontaneous and a non-spontaneous reaction, correlated the delta G value, and solved for the KEQ for both types of reactions, spontaneous and non-spontaneous. Okay, I am the Crazy Hat Chemist, and of course we can't end any video without a crazy hat. And I think this hat is actually too big to be shown in the screen, so I'm going to lower myself down and woo! Man, look at that hat. That's just a crazy hat. So if you like that video, give me a thumbs up. Please subscribe to my YouTube channel, and please pass on my YouTube channel to all your favorite chemistry friends and anybody that needs help in chemistry. If you go to my website, which is right there, okay, you can donate to my website so I can keep on making videos, get yourself a sticker, and maybe a cool t-shirt, which the logo my son made. Super cool, as well as the website. So I hope you have a fantastic day, and I got one more video on this unit here to tie this unit up, and I will see you next time. Bye for now.